In this video, I'm going to revisit the wine tasting study that was discussed in the foundation section of the non-parametrics chapter. So you may recall that 20 judges of wine tasted 10 different wines and gave a ranking to each wine. And the null hypothesis, under the expectation that people can't really discriminate between the qualities of various wines, is that the average rank across the 10 different wines will be equal within sampling fluctuations. And I tested this hypothesis with the Friedman's ANOVA, and that null hypothesis was rejected, which suggested that there's some level of discrimination that's systematic. Now I'm going to analyze those same data with one-way within subjects ANOVA. As I argue in the chapter on the basis of references, you can apply the one-way within subjects ANOVA on ranked data. So I'll go into Analyze, General Linear Model, Repeated Measures, and we have factor here. I'm just going to call that wine because there are 10 different wines. And we have 10 levels, so add, define, and I'm going to put the 10 wines into the within subjects variables box. Click on Options, Descriptive Statistics, Estimates of Effect Size, click Continue, and click OK. And here's the result I get. Here are the means associated with the ranks, and we can see that wine 4 has the highest rank, and from memory a higher rank indicated better quality. Now, just because there are differences in the means numerically doesn't mean there's a statistically significant effect, so we got to keep carrying on. Mauchly's test of sphericity is satisfied, which I believe will always be the case with ranked data. And here's the test of within subjects effects with sphericity assumed, an f-value of 2.14 and a p-value of 0.029 with 9 and 171 degrees of freedom. So I've rejected the null hypothesis of equal means, so there's something systematic going on, which supports the idea that to some degree, people can discriminate across the quality of wines in terms of the taste. And so the partial eta squared was estimated at 0.10, which suggests that 10% of the variance was accounted for, excluding any variance that was shared across the wines. Now, just to refresh your memory, this is exactly the same value obtained from Kendall's W. So go into Analyze, Non-Parametrics, Legacy Dialogues, K-Related Samples. Put the 10 wines into the test variables box, click on Kendall's W, click OK. And here is Kendall's W, 0.101, exactly the same as the partial eta squared, 0.101. Now the p-value associated with the Friedman test and also the Kendall's W test is equal to 0.033, and so the one-way within subjects ANOVA was a little more powerful because it's producing a p-value that is a little bit lower than 0.033. And this has happened a couple of times in the textbook now, where the one-way within subjects ANOVA on ranked data produces a more statistically significant effect than the corresponding non-parametric statistic. So that can be an advantage of the non-parametric statistic applied to ranks in comparison to the Friedman ANOVA, which is essentially applied to ranks as well. And there might be other advantages associated with conducting a one-way within subjects ANOVA. A practical advantage is that you have the opportunity to do post hoc testing. So if you go into Analyze, General Linear Model, Repeated Measures, Define, and then click on EM Means if you have version 25, or click on Options, and you'll see the EM Means information at the top of this window in versions before 25. But in version 25, EM Means, click, and then you can place your wine variable in the display means for and compare main effects, and then have a Bonferroni correction, and then you can compare all the means for statistical significance and protecting yourself. So here are all those pairwise comparisons. And you can see that none of the actual pairwise comparisons were statistically significant, which suggests to me that the Bonferroni correction is actually too strict of a correction in this case. And that's one of the challenges with omnibus within subjects effects, is that the options for multiple comparisons are not very plentiful, and they're also not very attractive. We have the Bonferroni. But in other cases, you'll find that you'll get statistically significant effects. This is a study where the effect is relatively small, and so any isolated comparisons with a Bonferroni correction are not being identified as statistically significant.